This job aid was produced by the National Weather Service Training Center to assist qualified NWS, DoD, and FAA electronics technicians in performing routine maintenance. This presentation will reference maintenance procedures from the relevant engineering handbook that was in use at the time of its production. The technician will refer to the most recent engineering handbook for current procedures, cautions, and warnings. Measurements captured in this video are from a non-operational site and should not be used for comparison to measurements at a field site.
Klystron transmitter tuning. In this procedure, we're going to cover how to tune the Klystron per paragraph 5.5.10 of the 6-511. It's all about the output. This procedure is going to set the output pulse that comes out of our transmitter. The goal is a 700,000 watt pulse. In sharp pulse, the rise time will be targeted at 150 nanoseconds. The 6 dB pulse width will be around 1.57 microseconds, and the long pulse width will be about 4.71 microseconds. Of note, we will make our adjustment of our pulse width based on the 6 dB point, and then we will measure the 3 dB point and put that information into the adaptable parameters of the software. The variables that we can control to get the pulse that we're looking for: we can control the pulse width that we put into the tube, we can control the turn-on voltage of the tube, and we can control the cavity tuning of the tube. Some things we need to consider. The first place we can measure the tube is 1AT4. This is several components downstream of the vacuum tube, so we're going to have to take those losses into consideration. When we hook up our test equipment, we're going to be measuring the power output of the tube and the pulse width, but we're going to be measuring these at the same time, which is going to be involving additional losses from 1AT4 to our test equipment. We're going to have to take those into consideration. Generally speaking, the stronger you turn a vacuum tube on, the sharper the rise time is going to be. The more we tune the cavities for more power, the sharper the rise time. Turning the tube on or making the cavities more productive reduces the pulse width and also sharpens the rise time. So we're going to need to balance these variables out, and that's what this procedure is about. The initial conditions for this is we should have verified our low voltage power supplies are looking good. Our filament current, our focus coil currents are correct, and alarms are set correctly. We've verified our RF drive into the tube is correct. We've ensured that the time we put the RF energy into the tube and the time that the tube turns on is correctly adjusted. And we've made sure that we trust our PFN meter. In doing the transmitter alignments, you've already probably done step 1, but if you haven't, you would need to gain control from the operations staff, put it to the maintenance staff at the RDA, and put the system in standby. We need to calibrate the power meter with a high power head, so let's make sure you're using the HP 8481H or equivalent. If you try to use the medium power head or the low power head, you will blow them up. And we should have a video up on the Training Center webpage for aligning a power sensor. In step 3, you're going to remove the center bay cabinet door. Be aware when you open up that center bay cabinet door, things will get very noisy in the shelter. You should be wearing hearing protection. You're going to need to locate the nameplate on the vacuum tube. It's normally over on the left, and get the manufacturer, the RF drive input, filament amps, focus coil amps, and the serial number documented, and locate a Klystron datasheet. The image on the far left is what the datasheet for an L3 looks like, and the center and right would be the front and back of the datasheet that's associated with a CPI vacuum tube. The datasheets contain voltages and currents that the tube is designed to operate at. In previous alignments, we were interested in the solenoid current and the heater current. In this alignment, we're going to be interested in the cavity tuning that has been determined by the manufacturer. So the manufacturer has tuned these tubes in preset frequency intervals, and we're going to use these numbers to preset our tube. If you're fortunate enough to have a site that's running on one of these even frequencies, all you have to do is come down to that frequency and transport those numbers from the data sheet into our procedure. Make note that cavity 1 is at the bottom, cavity 6 is at the top. So in this example, we've picked 2800 megahertz and we've moved the numbers over. If you're not so lucky and you've got one of these sites that are between the frequency, here at the training center we've got a 2768 system. So since there is no 2768 on the data sheets, we're going to have to interpolate it. So take the values for 2760 and take the values for 2780 and get the difference of them. And then since there's 20 megahertz difference between 2760 and 2780, we're going to divide that number by 20. And in this example, my system is 8 megahertz over 2760. I'm going to multiply that value times 8, and then I'm going to apply or add that number to the 2760 value to get my final preset value for the tube. Now the counters are in whole numbers and we're sitting here working this down to the tenths. Yeah, I get that. That seems a little tight. Generally speaking, the closer we are in our preset settings, the easier our tube is to align. It's rare, but I have seen where somebody did their presets so perfectly that there was no aligning of the tube. It's extremely rare. So after you figure these numbers out, we're going to write those down, and remember, 1's at the bottom, 6 is at the top. Now we're going to need to zero our cavities. We need to be consistent. We're going to take our wand, insert it into the cavity hole, and feel for the slot. It's like a flat tip screwdriver and a slotted screw. Once you find that insert, you're going to rotate fully counterclockwise until the tuning wand stops. Do not force it, you're just going until it gently stops. Different tubes have different feels to their stops. We want to be consistent in what we consider the stop on all the cavities. So once you come back to that stop, you're going to pull the knob out a little bit, disengage the gears, and rotate the counter to read all zeros. We're going to do this for all 6 cavities. There's a good note on how to do this in the book. Cavity counters may have as much as 1 full movement before a cavity is engaged. To compensate for this play, begin tuning the wand clockwise until resistance is felt. Once resistance is felt, pull the wand out slightly and set the counter for 0, 0, 0. Engage the tuning wand and continue with cavity tuning. Any offset from perfect zero will need to be accounted for when setting the cavity. My advice is to be consistent. And they would have you take your interpolated numbers from step 6 and set the cavities to those values. And here's an example of setting cavity 6. We're using cavity 6 only because the angle for the camera was best. And we've got our tuning tool engaged with the tuning cavity. And we're going to turn counterclockwise until we find resistance. Once resistance is felt, we'll take our slack out, lift and disengage the gears, set our gears to 0. If you engage it and you find you're not quite on 0, we'll just take it out and try again. Once we've got them on 0, we're going to go to our preset value. And in this example, we're going to go set it for 42.2, our approximation of that. And there it is. And now we're at our decision point. If the tube was just replaced, we're going to do paragraph 5.5.10.2. If we're retuning a tube that was already in the transmitter, we'll go ahead and proceed to paragraph 5.5.10.3. If this is a new tube, we're going to run it for a little while and let it warm up slowly while we're drawing down the vacuum current as displayed by the vacuum meter. First thing we'll do is turn our auxiliary breaker on. This will fire up the filament power supply, which will start heating up the tube. We'll set the high voltage breaker to on. There's a note that during this procedure, we may be generating some alarms. This is not a big concern. It happens. In step 3, we'll record the initial vacuum pump current via the vacuum pump current meter and microamps. About 12 minutes after the auxiliary breaker was turned on, the preheat lamp should go out. If all is well, the available lamp will come on. We need to check our vacuum pump current and make sure it is under 10 microamps. If it's not, we're going to wait a little bit longer until we get under 10 microamps before we proceed. The next thing we want to do is record our RF drive attenuator dial setting. The reason we're going to record this is we're going to turn our RF energy into the tube down to minimum. And we're going to run this tube with minimum input to get minimum output out of the tube. And step 6, they have us rotate the attenuator fully counterclockwise. Here at the training center, we found multiple attenuators that turning them counterclockwise did not give us full attenuation. It gave us minimum attenuation. In those attenuators, we needed to turn them clockwise. So to determine whether we needed to go clockwise or counterclockwise, we could check the power going into the tube from the attenuator and turn in the appropriate direction. The best reference for this would be paragraph 5.5.8.3, the RF drive procedure, and we will want to do the procedures that are referencing the power and not do the steps that are measuring the pulse width. That said, if you just want to be thorough, you can go through and do the whole procedure again. Just don't adjust your pulse width. As this recording is being made, steps 4 through 25 are the steps that cover the pulse width. Once our attenuator is set for maximum attenuation, we're going to adjust our PFN control potentiometer 3 turns fully counterclockwise. So we're going to reduce our PFN voltage considerably. We'll open up our system test software via our RDA human computer interface, go over to the control drop down and select AME receiver control. From the test source drop down, select Klystron output, verify sharp pulse, PRF of S1, and inject the signal. Your transmitter will start running. We're going to leave it at this for 20 minutes. After 20 minutes, we'll rotate the PFN potentiometer A1R3 one full turn clockwise. And then we'll wait another 20 minutes. And then we'll rotate the potentiometer again, one full turn clockwise. Finally, after an additional 20 minutes, we'll adjust the A1R3 to set the PFN voltage for 4.6, which would correspond to 4600 volts on the PFN meter. At this point, we can return our RF energy going into the tube to the original setting that was noted in step 5 and allow the system to run for another 20 minutes. Verify that your focus coil current is equal to the datasheet value or nameplate value plus or minus a half an amp. And then after this 20 minutes, we're going to shut the system down by changing our test source drop down to none, injecting signal, and we're ready to proceed to paragraph 5.5.10.3. Paragraph 5.5.10.3. First thing we're going to do is we're going to measure the equipment test path loss. We're trying to get 700,000 watts out of our transmitter. The first place we can measure that is at 1AT4. Establishing our loss from our tube to 1AT4 is simply a matter of adding up a bunch of losses that are documented in the adaptable parameters of our software. We'll need to establish our loss of our test equipment, or the loss from 1AT4 to where our power head is when we're doing our tuning of the tube. To do this, we're going to use the Klystron's output as our standard input. Steps 1 through 4, we'll take the power at 1AT4 and establish it as our standard. Steps 5 through 9 configure our test equipment. We'll be taking a N-type cable, connecting it to a 6 dB medium power attenuator that will feed a 4-way splitter. Off the 4-way splitter, we're going to have a terminator, a variable attenuator feeding a spectrum analyzer, a 20 dB fixed attenuator feeding a 0 to 11 dB variable attenuator that we're going to use to measure our pulse width via a crystal detector into the oscilloscope. And we'll also have our power sensor plugged into this 4-way splitter. we need to establish what our loss is between the power sensor when it's plugged into this 4-way splitter and when it's plugged in directly to 1AT4. Step 10 will measure that power at the 4-way splitter, and this will give us our test equipment loss. So this is the procedure step by step. Step 1 is connect your high power head to 1AT4. Go to your system software, go to the control drop down, select AME receiver control, select your test source as Klystron output, verify you're in short pulse, PRF is S1, and inject the signal. Transmitter should start operating, and we're going to need to adjust our pulse forming network voltage to 4.6 kilovolts. Our PFN meter should read 4600 volts. At this point, we don't want to make any more changes between the measurement in step 4 and the measurement in step 10. So you want to make sure you make this adjustment before you read your power meter. We'll do the math in step 20, and we'll make our measurement at 1AT4. In step 5, we'll turn our tube off by selecting test source of none and inject signal. We'll disconnect our power meter from 1AT4 and connect our test equipment per figure 5-6. Build this like figure 5.6, not the simplified training center drawing. We're going to set our variable attenuator to 6 dB. That'll be our first pulse width we're going to measure. And then we'll fire our tube back up with the Klystron output as our test source. Pulse width should still be in shorten 1, PRF should still be S1, and we'll inject our signal. At this point, we're going to measure the output of the 4-way splitter. With our input known in step 4 and our output known in step 10, we can now figure out what our loss is of our test equipment. At step 10, if you find that you're below scale, the most common reason for that is we've messed up something on our cavity pre-tune. So don't panic, just go back, select test source of none, inject signal, and go back to where you pre-tune the cavities. You're going to have to go back and remeasure step 4 and remeasure step 10. If you feel there's a significant change in the output power of your transmitter between step 4 and step 10, that's not a problem. Go ahead, let your power meter stabilize in step 10. Once you're comfortable that it's stable, record the measurement in step 10 and quickly select the test source of none, inject signal, remove the cable, put your high power sensor on 1AT4, select test source of Klystron output, and inject signal. With 2 people, that's something you can do really quick and ensure that you're making those 2 measurements with the tube at the same temperature. The important thing is that we have nothing change between step 4 and step 10. In step 11, we're going to adjust cavities 1 and cavity 6 to get the peak power as observed on the power meter. Generally speaking, most people find very little power to be picked up there, but we need to check to make sure those cavities are at their peak. The next few steps are going to use the oscilloscope, so we're going to need to make sure our oscilloscope's set to 50 ohms and triggered appropriately. If you're using a digital scope, it'll trigger off the signal just fine. An analog scope may or may not, and you can use RF pulse start if you need to. Adjust your voltage division somewhere between 10 and 50 millivolts a centimeter, and your time division should be about half a microsecond. The procedure doesn't know if you're using a positive or negative crystal detector, so your rise time may indeed actually be a fall time if you were using a negative crystal detector. You should see a waveform similar to figure 5-8. Next, we're going to measure the rise time. If you're using an analog scope, you want to set the base at 0% and then use your variable voltage per division knob to adjust the peak to 100%. If we adjust our cavity 4 to adjust our rise time, you'll find that your amplitude will change, so your 100% point will change, and you'll have to come back and catch that and correct for it. And then you're going to use your cursors to measure the difference in time between your 10% point and your 90% point and record that rise time. If you're using a digital oscilloscope, we can just select the measurement for the channel we're looking at, select rise time, and make sure our reference levels are set for 90% for the high reference and 10% for the low reference. The beauty of the digital oscilloscope is as we change our amplitude of our signal, the digital oscilloscope will track with that, and we will not have to readjust our oscilloscope. So we'll measure our starting rise time, step 14, whether we're using an analog or a digital scope. And we're going to show you an example here. We're using a digital scope, so it's not marked with the 10 and 90 or the 0 and 100s. We're just going to have to use each division's equal to 20%. First thing we're going to need to do is we're going to need to get our waveform to equal 5 divisions to represent 100%. So we're going to select our variable amplitude, and we're going to set it for 5 divisions. And we'll call this 100%. Once our amplitude is set, then we need to measure our horizontal time base, so we're going to select cursors. In this example, we're using paired cursors to mark the amplitude along the waveform. So we're going to go halfway up our first division, representing 10%. And then we're going to measure the 90% point, half a division between the 80 and 100, or between the 4th and 5th division. And we've got our 90% measured. Now we're not moving our cursors, so that measurement's static, and you see it's showing 150 nanoseconds. Our automatic one is currently moving around a little bit because it is moving with the waveform that it's measuring. And now we'll demonstrate setting up the automatic measurement. First thing we're going to need to do is select the measure menu, and then hit the button for select measurement for channel 1, and then select rise time. And now we're ready to tune cavity number 4 to give us a rise time of 150 nanoseconds, plus or minus 25 nanoseconds. When we have a longer rise time, we have a more softer, smoother waveform, and then as we get a sharper than 150 nanoseconds, we tend to get a very sharp waveform that will eventually turn into Batman or fold over. So we want to be back near 150 nanoseconds. We're looking for a pulse that is somewhat squared, but it's not hard, sharp squared. It's a pulse that has a bit of rounding to it. What they're looking for is what we've got here in figure 5-12. And now we're going to do a little video showing you what that looks like. As a result of our pre-tune, we're starting out somewhere around 240 nanoseconds. We will insert our tuning tool into cavity 4 and begin tuning to 150 nanoseconds. Notice the waveform is getting larger in amplitude. So if you're doing the manual rise time adjustment, you would have to take that into consideration. And we fine tune it for 150 nanoseconds. Now that the rise time is set, it's time to verify our 6 dB pulse width, adjust it if necessary, and then measure our 3 dB pulse width. The idea is to put the pulse on the screen with the top of the pulse on the center gradical. We'll then remove 6 dB from the circuit. The pulse will rise. The points where the pulse crossed the center gradical is the pulse width for 6 dB. You can then use your vertical cursors to measure the point where the waveform crosses the center gradical. If the pulse width needs adjusting, you'll adjust it using the pulse shaper and measure again if needed. At this point, we'll add 3 dB of attenuation back into the circuit. The pulse will now cross the center gradical at the negative 3 dB point. We'll measure this and use it for calculations and as inputs for the computer. We'll look at a video of this before we go through the steps. With our variable attenuator set to 6 dB of attenuation, we're going to adjust our waveform until the top of the waveform is running along the center radical of the oscilloscope. Once we're satisfied with that, we're going to remove 6 dB of attenuation from the variable attenuator. When we do this, the waveform is going to rise and go off the screen. At this point, we're going to select the vertical cursors, and then we're going to adjust one of the cursors until we mark the point that the waveform crosses the center radical. Once you've done that, we'll do the same thing for the other edge until we've got both edges marked, and this shows us our 6 dB pulse width. At this point it's showing 1.57, so now we're going to add 3 dB of attenuation to measure our 3 dB pulse width. We do that. The point in which we cross the center radical changes, so we need to change our cursors. So we'll adjust our cursors, first on one edge and then on the other edge. And now we've got our 3 dB pulse width. And in this example, it came out to exactly 1.5 microseconds, or 1500 nanoseconds. And step 16 is to measure our pulse width by performing the following. Adjust your oscilloscope so that the peak of the pulse is running along the center radical. We'll then remove 6 dB from the variable attenuator. When we do this, our pulse will go off the screen. Do not adjust the oscilloscope for that, or the attenuators. That's what we want. Adjust your vertical time cursors so they mark the point at which the waveform crosses the center radical on both the leading and trailing edge of the center radical. The difference between the point where we cross the leading and the trailing edge is our 6 dB pulse width. If it is not 1.57 microseconds, then we'll adjust it by adjusting the pulse shaper narrow adjustment. Once we're satisfied with the 6 dB pulse width, we'll add our 3 dB attenuation via the variable attenuator back into the circuit and measure the pulse width just as we did before, where it crosses the center radical, and that will give us our 3 dB pulse width. The next step is to determine our path loss from the Klystron to our test equipment. And we've represented that in the green components in this drawing, and we're determining our loss between the Klystron itself and our test equipment that's represented in gold. We're going to go into adaptation data via our system test software. On the top, find the View button. From its drop down, select Adaptation Data and AdaptCur.dat. AdaptCur.dat is the adaptable parameters that your system is currently running on. From the adaptation data, click the Transmitter tab and record the values in Step C. Once you've got those values, close that window. The values will be added together in Step 18. On the screen here, we're showing you that TR17 is your path loss through the arc detector. TR18 is your path loss through the harmonic filter. TR19 is a path loss through the circulator. If you've got a spectrum filter, it's represented by TR20. There is a miscellaneous loss, or correction, called TR21. The path loss through your directional coupler is TR23, and the path loss through 1AT4 is TR32. And here's a graphical representation with the adaptable parameter numbers associated with the devices that they represent. Now that we've got that information, we're going to calculate our path loss of our test equipment, the component shown in gold on the screen. So the first thing we're going to do is we're going to note the power that we're currently reading on our power meter coming off the four-way splitter. Then in step 20, we're going to take our measurement that we made at 1AT4, step 4, and subtract the measurement that we made on step 10, which was the output of our four-way splitter. This will represent the loss that we have of our test equipment. We've determined our 3 dB pulse width in step 16, and we'll use that along with table 5-4 to determine our duty cycle in dB. Note that there's a crystal set reference in the left side of this screen. Most systems that are single thread, not redundant systems, will be running crystal set C. On redundant systems, you'll be running 2 different crystal sets. To determine which crystal set you're using, you can look at your adaptable parameter TR4. Now that we've got some information together, we're going to figure out what our meter should read at the four-way splitter when we have 700,000 watts coming out of the Klystron. 700,000 watts is 88.45 dBm. We're going to add our duty cycle as a negative number to the 88.45, along with our loss from the Klystron to 1AT4 and our test equipment loss. This will give us the reading that our power meter should read when we have 700,000 watts peak power coming out of the Klystron. In step 23, we're going to adjust our PFN voltage to get the number that we just calculated for our power out of the four-way splitter. Do not exceed 5200 volts. 5200 volts is getting very close to the alarm limits of the pulse forming network. When you make this change, you will probably affect the rise time. In step 24, they have you go back and verify your rise time. If it's outside of specifications, they suggest you adjust cavity 4 till the rise time meets specifications. Adjusting the rise time will affect your output power as well. And in step 25, they're having you recheck your pulse width to make sure it still measures what you did in step 16. If the pulse width is changed, you need to repeat steps 21 through 23. It sounds like something that could get into a vicious loop. It's not that bad. You may need to come around this loop once or twice, maybe 3 times, to get everything in balance. After we've made these changes to our tube, we need to go back and remeasure the 3 dB pulse width as you did in step 16 and record this in step 26. This will become transmitter adaptable parameter TR5. At this point, we need to make the same measurement for long pulse. So we're going to go to the AME receiver control window in the software and change short pulse to long pulse. Verify that you're in PRF S1 and inject signal. You'll hear your PFN switch change over and your system will restart in long pulse. Your waveform will probably go off the screen and you'll need to adjust your horizontal time base. At this point, we need to check that our 6 dB pulse width in long pulse is 4.71 plus or minus 0.1, and then we're going to measure our 3 dB pulse width. The method for making the measurement and adjustment is exactly the same as we did in short pulse. The only difference is the pulse width involved. So you're going to adjust your oscilloscope such that with the 6 dB attenuation in place, the top of the waveform goes across the center gradical line. Then we'll remove the 6 dB from the variable attenuator, and then we're going to adjust our vertical cursors so that they mark the leading and trailing edge of the waveform as it crosses the center gradical line, just as we did in sharp pulse. We should measure 4.71 plus or minus 0.1 microseconds. If not, we'll adjust our pulse shaper with the wide adjustment. Once satisfied with this measurement, we'll add 3 dB to our variable attenuator and measure the 3 dB pulse width, just as we did in short pulse. At this point, we need to determine the duty cycle for long pulse with the pulse width we just measured. Use table 5.5 and the pulse width from step 29 to determine your duty cycle in dB. Be aware of the crystal set that you're using on your system. And once you've done that, put it down on step 30 and we move on. Now we need to do the same thing we did in short pulse, we're going to do in long pulse. 700,000 watts is 88.45 dBm. We're going to add the duty cycle as a negative value, our loss to 1AT4 as a negative value, and our path loss of our test equipment as a negative value. The sum of these will give us the expected power at our four-way splitter when we are generating 700,000 watts peak power. At this point, if we do not have that value, we're going to adjust A1R3, your PFN voltage control potentiometer, to increase or decrease the PFN voltage until you get your target power measurement. This is the same adjustment you made for the short pulse. There is a bias adjustment that we will use to correct the adjustment for both short and long pulse using the same potentiometer. Again, do not exceed 5200 volts. They normally expect it to run around 4800 volts. Once you've got the correct power coming out of your four-way splitter, measure your 3 dB pulse width again, same way you did in short pulse, and this value will be our TR6 value. At this point, we'll turn our transmitter off by selecting Test Source None and Inject Signal. We're going to open the inner bay door on the left. When we do that, we're going to get an interlock alarm. That's normal. We're going to insert our interlock bypass tool into switch S4, and that will give our system a complete interlock circuit, and we'll clear the fault display to clear the history, and we'll locate on the back of the inner bay door on the lower circuit board, locate A1, A2, R74. It should be just left of the lower D-type connector. Make sure you are on the correct potentiometer. At this point, go back to your AME receiver control window, go to Klystron output, select short pulse. You'll hear your PFN switch. Make sure your PRF is set to S1 and inject signal. When you do this, the transmitter will come up and start running. If the output power is different than it was before, the only thing we've changed between short pulse and long pulse was the PFN voltage. A1, A2, R74 will adjust for that, and you will adjust A1, A2, R74 until you get the output power at the output of the four-way splitter to be the same as what you had previously before you made your long pulse adjustment. Once you've got that, change your test source to none and inject signal to turn your transmitter off. Remove your interlock bypass tool from the door interlock and close the left inner bay door. When you turn the key, you'll re-engage the interlock. You'll hear the big relay engage, and the system will have an alarm for about 5 seconds while it resets itself. At this point, since that was an error that we induced into the system, we'll clear it from our history with a fault display reset and disconnect all our test equipment. Anytime we change the output pulse of our transmitter, we need to run the IFDR alignment procedure. That can be found in the Engineering Handbook 6-513, Section 6.5. We've got a video on that at the Training Center webpage, and we'll include that at this point in this video.
Paragraph 6.5.11, Intermediate Frequency Digital Receiver Alignment. This procedure adjusts the digital signal processor's finite impulse response matched filter based on the characteristics of the transmitter burst pulse, optimizing the receiver to obtain the best possible burst pulse sample. Any adjustments made to the transmitted pulse require the IFDR alignment to be reaccomplished. The FIR filter parameters specified in this procedure are optimal for a transmitter aligned per EHB 6-511. If any part of this procedure does not fall within limits, you should verify the transmitter power and pulse shape. Perform steps 1 through 2B of Table 6-9 to place the system in standby state. At the main RDA HCI, click System Test Software and Yes. In the System Test Software window menu bar, click Calibration IFDR Configuration. In the IFDR configuration window, the burst pulse tracking area will display Disabled. If not, click on Enabled to change to Disabled. In the IFDR configuration window, click on the Plot Burst Pulse tab. Adjust the windows for best visibility. The DSPX scope displays the burst pulse, and the IFDR configuration window displays the plot burst pulse controls. The burst pulse plot is a time domain display of the burst pulse signal, similar to how it would appear on an oscilloscope. Below that are a number of traces, some of which display the triggers produced by the IFDR, which are sent to the SPIP for distribution to the transmitter. Not all of the triggers will be visible due to the span of the plot. The plot burst pulse controls will be used to optimize the display and adjust trigger timing to center the pulse in the filter, synchronizing it to T0. Plot time span adjusts the span of the DSPX scope display. Amplitude zoom adjusts the amplitude of the burst pulse plot. If the burst pulse is not centered in the middle of the DSPX scope window, use the Shift Triggers right and left arrow buttons to center the burst pulse within the aperture window. The pulse is centered when the large tick marks at the bottom and top of the aperture window are resting on or close to the center vertical line of the DSPX scope window. The Shift Triggers control shifts all the triggers at the same time to sync the transmitter triggers with the IFDR timing. The burst pulse frequency should be 57.5 plus or minus 0.5 MHz. If burst pulse frequency is outside of tolerance, perform RF generator checkout per para 6.5.12. At the IFDR configuration window, click on Plot Burst Spectra tab. The DSPX scope will open displaying the burst pulse spectra, and the IFDR configuration window will display the burst pulse spectra controls. The burst pulse spectra plot is a frequency domain display of the burst pulse similar to how it would appear on a spectrum analyzer. The controls will be used to optimize the display and adjust the impulse response length and bandwidth of the filter to pass the burst pulse. Click on the Plot pull-down menu and select Burst Spectrum and Receiver for Filter Response. Set samples to 10 using the Burst Pulse Samples down or up buttons. While observing the taps and fur fields, use the Impulse Response Length smaller and larger buttons to set the taps to 220 with a fur filter length of 2.29 microseconds. While observing the DC gain and filter bandwidth fields, use the filter bandwidth arrow buttons to achieve the optimal DC gain of 0 dB and a 3 dB filter bandwidth of 0.714 MHz. If the bandwidth is significantly incorrect, use the large increment controls to get close to the optimal bandwidth, and then use the small increment controls to get to the optimal values for both filter bandwidth and DC gain. Nominal loss values are negative 0.50 for short pulse. If a higher loss is noted, the transmitted pulse may be slightly degraded and not match all of the desired characteristics defined in the transmitter manual. However, the short pulse loss measured through this procedure is considered correct based upon the pulse as it exists at this point and should be used in adaptation data at this time. To update adaptation data R41 for short pulse, click on the Update Adaptation Data button. At the Confirm Adapt Data Items Changed pop-up window, click OK. At the Adaptation Data Updated pop-up window, click OK. In the General tab, then click Short Pulse in the pulse width area to change to Long Pulse. In the IFDR configuration window, click on the Plot Burst Pulse tab. Use Shift Trigger's right and left arrow buttons to center the burst pulse within the aperture window. In the last few software versions, the center of mass tracking has not worked for long pulse, so aim for centering the pulse in the window. Verify the burst pulse frequency is 57.5 plus or minus 0.5 MHz. FDR configuration window, click on Plot Burst Spectra tab. The DSPX scope will open displaying the burst pulse spectra, and the IFDR configuration window will display the burst pulse spectra controls. While observing the taps and fur fields, use the impulse response length smaller and larger buttons to set the taps to 520 and the fur filter length to 5.42 microseconds. While observing the DC gain and filter bandwidth fields, use the filter bandwidth arrow buttons to achieve a DC gain of 0 dB and a 3 dB filter bandwidth of 0.252 MHz. The nominal loss value is negative 0.15 for long pulse. If a higher loss is noted, the transmitted pulse may be slightly degraded and not match all of the desired characteristics defined in the transmitter manual. However, the long pulse loss measured through this procedure is considered correct based upon the pulses that exist at this point and should be used in adaptation data at this time. Anytime transmitter alignments are performed that affect the transmitted pulse characteristics, this procedure should be repeated. Click on the Update Adaptation Data button. At the Confirm Adapt Data Items Changed pop-up window, click OK. At the Adaptation Data Updated pop-up window, click OK. Close the IFDR configuration window by clicking Closed. Close System Test Software window by clicking File, then Exit and Yes to confirm. Click OK on the Elapsed Time pop-up window. Restart the RDA software to ensure the updated values for R40 and R41 take effect by performing the following steps. At the main RDA HCI, click RDA, Restart RDA SC. In the Confirm Restart RDA SC pop-up window, click Yes. The main RDA HCI grays out and the RDA Connection Lost window appears. After the RSP reboots, log back into the system if necessary.
And after we complete the IFDR alignment procedure, we need to update TR5 and TR6. And we'll do this by opening up our adaptation data, view, adaptation data, adapt.cur, just like we did before. And that'll give us our transmitter page. On our transmitter page, we're going to change the values for TR5 and TR6. When we click the Submit button, we'll get a confirmation to pop up. We'll say OK to that, and then we'll get a pop-up to remind us that we have to restart our software in order for the values to take effect. And now we've updated TR5 and 6. If you need a reference, step 44 tells us the 6-513 paragraph that'll tell you how to do what we just did. In order for the software to use the new values, we need to restart the application software. We would close the system test software, go back to the main RDA human-computer interface, click RDA, restart RDA SC, and then click Yes to confirm the restart. The software will restart, and when it restarts, we'll be ready to continue. The next few steps are going to ensure that the 4A26 power meter in the receiver cabinet agree with the power that you measure at 1AT4 with an external power sensor. So we're going to use a high power sensor on attenuator 1AT4. You're going to return to your system test software, control AME receiver control, go back to test source of Klystron output source, ensure shorten 1, S1, and we'll inject the signal. Let your power meter stabilize. Once you've got that power measurement made, we're going to select test source of none and inject signal to turn the transmitter off. At this point, we'll disconnect our power sensor and reconnect W61-161 to attenuator 1AT4 to give us an RF path to the built-in power meter. In step 52, we'll go to the calibration drop-down and select transmitter power. We'll ensure that we're looking at the sharp pulse. We'll click calibrate scale. It will prompt you for the measurement that you just made of the output power measured at 1AT4. You'll input that, select OK. It will then run the transmitter, see what the power is that it measures on 4A26, and then give you a pop-up to show you the difference in what it measures and what you measured. It has calculated a new meter scale. The output of that power meter is a DC voltage that goes to an A to D converter, and you're changing the value of the steps of the A to D converter. You will accept that. And just as before, it won't take effect until the software is restarted. From the human computer interface window, we'll select Backup Restore. You'll get a pop-up. There'll be several tabs. There's an Archive File tab, a Backup Files, and a Restore Files. While the procedure is referencing making backups, in the Backup Files tab, the Archive Files tab will also back up the log files. With the Backup Files tab, you're going to be backing up what is necessary to run the system. If you select the Archive Files, you'll also be backing up the logs. These logs will include alarms and adaptable parameters logs. So any changes that were made during the alignment procedure will be included in the log for adaptation data. This could be helpful if you've made a mistake, put a comma instead of a period, or mistyped something. You would be able to track it by seeing the listing of the logs that were changed. Once you've decided which way you want to go with this, put a CD in the CD drive, close it, and hit Burn CD. Step back and let it do its thing. You'll see an update window run for a little bit. The CD drive will open, extend, and then go back in before it completes. So when you see the drive open up, don't grab it immediately. And when we finish making our backup, step 54 will have us update our transmitter parameter and adjustment record card to show what we have for our normal values as your system is operating currently. And this ends this paragraph.